All right, folks, we're going to take a look at these notes on two-dimensional motion. And the biggest thing that you're going to see here, there will be similarities or relationships from one-dimensional motion. So when we were talking about velocity or acceleration, this gets a little bit into vectors also. Newton's laws are definitely still applied. But the biggest thing that you're going to see here is that we kind of analyze two things at once. And this relates a lot to things you would see in math class. You think of the vertical and the horizontal component, or, you know, the x and the y component. This first demo here, all that I'm trying to show you is the vertical component of an object in free fall or becoming a projectile is 100% related to just gravity. So when something is under the force of gravity, it always wants to be pulled down toward the earth. Now, that doesn't mean that an object that is in free fall necessarily has to be falling toward the earth, but this is probably the most common example. So in this first situation, person is on top of a cliff, an object is at rest, and they release it to fall to the ground. Let's just assume at the top of this object is not moving at all. It's at 0 meters per second. And for simplicity, we're going to assume that at the top of this arch or at the top of this arch also is also going to be 0 meters per second. We're going to say the vertical component, which a lot of times is referred to as your v of y, at this point is going to be stationary or motionless. So at the top of the arc, hasn't fallen yet. In this situation, it's been thrown to the peak, momentarily pauses before it starts to fall back to the ground. And even though this arch is on kind of a different path, it's still at the peak, the vertical motion of it becomes 0. For objects that go straight up or straight down, there is no v of x. This does not move left or right. But as it moves further and further down, it accelerates and moves faster and faster until it hits the ground. We'll just keep the numbers simple for now. I'm going to say somewhere in here it's going like 5 meters per second. And I'm going to say somewhere down here, maybe when it hits the ground, it's going 20 meters per second, up until that moment when it smashes into the ground. Assuming that these heights, and again, we'll try to keep a lot of these variables the same. Let's just assume that the height, if you were to drop an object from 10 meters, whatever velocity it obtained by the time it hit the ground, and in this scenario we're going to say 20 meters per second, if I wanted to throw an object up to that same height from the ground, this whole equal and opposite thing would still hold true. At the bottom, we would need a vertical velocity, or a v of y, that is equal to 20 meters per second. It would be the same thing here also. If the v of y going up or the v of y going down, these would all have to be 20 meters per second. Okay? That's constant. Constantly changing, so as you go up, opposite like when we were going down, if the top was 0, if we were at some given height here, this would be 5 meters per second going up. This would be 5 meters per second going down for the given height. Now the horizontal component comes in. Example 1, there is no horizontal component because this object's being dropped straight to the ground. This object's going up and down, and you can see there's a little bit of horizontal motion. This v of x, assuming we have no air resistance, which for the application of the problems we're going to work with, we are going to assume that there is no air resistance. So whatever the horizontal component was here, they're going to call it v of x. If this was, let's just say 1 meter per second, it would be 1 meter per second the whole time until it came in contact with the ground. So even here, as it's moving over, it would be 1 meter per second. In this example, you can tell it moves to the right more. We'll just call this v of x, I don't know, we'll call it 3 meters per second. It remains 3 meters per second all the way. V of y on the way up, we would say was equal to 5 meters per second. And then on the way down, this v of y here would be equal to 5 meters per second. It's a little tough to draw all that in. Very top, we're going to, again, we'll set some common height here. I'll say is just equal to 10 meters from where the cannonball is launched all the way down to the ground. We're going to start with one variable. We'll say v of x. Let's just say that this cannon launches a cannonball out of here at 20 meters per second. The path of projectiles, or the trajectory that these objects take, typically follows like a curved line from top to bottom. We're going to have a v of x and a v of y at each of these locations. With that said, These are the shapes of projectiles. They typically take curved paths. The shape of the path is called trajectory, which you can see down here. And we're always going to label them with two components for velocity and also for distance. And I'll get into that a little bit later as we do more examples. But we do the horizontal distance, we call d of x, goes from here to here. That is also known as the range, how far a projectile goes. So often we'll talk about, the range of this. If you were to throw something or punt like a football, we'd talk about what is the range that you could actually launch it as. And the height, going from bottom to the top or from the top just straight down, depending on what type of projectile we're talking about. If this is d of x, then this is going to be the same as d of y, which is also known as the height. But the definition for acceleration when we're dealing with things that are spinning in circles is v squared over r. So it's really important to kind of understand that concept. Now, where these variables come from is important. So when we look at a diagram, the r, or the distance, is the radius from the center of the circle to the center of the mass, and the velocity would be the tangent or perpendicular velocity at the edge of the circle. If I was to cut this string and this object were to just travel in a straight line, what would the distance be? Now, when you go around a circle, velocity is still distance divided by time, but distance is the length of the edge of the circle, which would be known as circumference. So when you go around this outer edge, if we wanted to kind of manually calculate the velocity, you'd have to do the distance of 2 pi r. So the equation for force could be looked at in a few different ways. The base equation for force, mass times acceleration. Mass is just mass, the amount of matter in an object. So if this is, say, 5 kilograms or whatever, pretty easy to just look at it and say 5. And the acceleration, they maybe will give you in some problems. They might just tell you that the centripetal acceleration is equal to, and then give you a value. But a lot of times they might actually just give you the velocity of the object and then the radius, and you'll have to calculate it. So all we're doing from here to here is substituting in this v squared over r. These are just some basic, again, geometry things to figure out a distance of a circle and then divide by time. So it's bringing it back to kind of primitive thought processes. What we're really looking at here is centripetal and centrifugal forces and or accelerations. So they are kind of one of the same, but really they're kind of opposites, and one of them in a lot of descriptions is described as a non-existent force. The one that is definitely true is anything that spins in a circle needs to have a center-seeking force, and this would be known as the centripetal force. So the force that's actually pulling it in. To memorize this, think of pedaling a bike, or pedaling, a bicycle wheel. You're putting all of your energy into where the crank is, or the center of the wheel. You're spinning around and putting your energy into it. So the centripetal force is this way. And the other one, which sounds similar, but I think is often mispronounced, is centrifugal force, or centrifugal acceleration, and that would be the outward seeking force. So centripetal force is the inward, and this is the outward. And sometimes people say that this outward force is kind of non-existent because as something's spinning around, let's assume you just have a ball on a string and you spin, spin, spin. You're pulling on the string and keeping this turning. Yeah, true, but the tension in the string pulling outward is kind of like that opposite force. And remember, according to Newton's third law, forces act in pairs, so there's got to be an action-reaction force to it. So this centrifugal force is kind of the outward force. So if we said there was an inward force of 500 newtons, I guess you could say that outward force is kind of like a negative 500 newtons. So the net force in that direction on the string, the tension in the string, would kind of always be 0, which is why the object would remain at a constant distance radius from the circle. So what we're going to do in these problems is we're going to do some calculations using the equations that they just gave us. And when we do any of this work, I always tell people to list the variables and identify the equation that you're going to use, then solve. So first example says there's an object moving at 2 meters per second around a circle. So I'm going to list the velocity of 2 meters per second. Moves around a circle that has a radius of 4 meters. So the radius is equal to the r, so there's the 2 meters. and it has a mass of 6 kilograms, so m equals 6 kg. They're asking what is the centripetal acceleration and what is the centripetal force. We could do this all in one step to find the force. We know force is mass times acceleration, but for application here, we're going to just do the acceleration, centripetal acceleration first, and the equation for that is v squared over r. If the v is 2, I'll neglect the units here just to show the math a little bit easier. So this is 2 squared divided by the radius, which is 2. Make sure you follow order of operations. 2 times 2, you do the exponents first before we divide. 2 times 2 is 4. 4 divided by 2 just gives us 2. And the units for acceleration are meters per second squared. So now that we have that, if we want to figure out the force centripetal, we just do the mass times the centripetal acceleration. So the mass is 6 kilograms, and we know that the centripetal acceleration is 2. So that gives us 12. And the units for force would be newtons. And example number 2, they're asking how fast would an object with a mass of 3 kilograms need to be traveling in order to produce a centripetal acceleration of 20 meters per second. If it was traveling in a circle with a radius of 5 meters, then they say what would be the centripetal force. So this is kind of working things backwards a little bit, but again, follow the same process. List what they give you. They give us a mass of 3 kilograms. They know that the force centripetal is equal to 20. Or sorry, the centripetal acceleration, so acceleration centripetal, here it is equal to 20 meters per second squared. And they're saying that the radius that it's traveling around is equal to 5 meters. They want us to figure out the centripetal force. And they want us to figure out the velocity. So a few ways that we can look at this. The velocity, acceleration, and radius. We have acceleration and radius, and we need velocity. So I'm looking at this equation. It has a, v, and r, acceleration, velocity, and radius. If you're given 2 of the 3, you should be able to rearrange an equation to solve for the other unknown. That's kind of what we got, a of c and r. We're solving for v, so I'm going to rearrange this equation. First thing I do is multiply both sides by r. So I got r times a of c would give me v squared, and then I would have to square root both sides to get the v by itself. So this is the equation I got to figure out the velocity. Once we have that, we can figure out the centripetal force pretty easy. Actually don't even need the velocity for that part because we got mass and acceleration here. But we'll solve for v first. R is 5, centripetal acceleration is 20. 5 times 20 is going to give us 100, and the square root of 100 works out very nice, 10 meters per second. And there's your velocity. Force centripetal is equal to mass times acceleration centripetal. Force is equal to mass times acceleration here. We have both of those values already. So the mass is 3 kilograms. The acceleration is 20. So we know the force centripetal, 3 times 20 would give us 60. So 60 newtons. Last example, talking about launching a cannonball off of the edge of a cliff. Has an initial horizontal velocity of 20 meters per second. Assuming there is no friction, how far will the ball travel? All right. So there's a couple things we got to look at. We're trying to figure out the range, or the d of x. We need a velocity and a time to figure out a distance, right? They tell us it's launched with an initial horizontal velocity of 20 meters per second. And again, remember, if it starts out at 20 meters per second, the whole time, as long as we do not have any wind resistance, even up until it hits the ground, is going to be going 20 meters per second. We don't really care about the vertical velocity right now. In some applications, we maybe would. All we really need in order to figure out d of x is v of x multiplied by time. Time is just time. The time of vertical falling is the same as the time of the horizontal motion. So what we really need to find is how long would it take for an object to fall from 40 meters, because that is the height. Since the vertical velocity is 0, we can use this wonderful equation. Looks like this. The square root of 2h over g. And we'll plug in our values and see what we get. So we got 2 times 40 divided by 9.8. And this gives me a time of 2.85 seconds. And we know that the original velocity is 20 meters per second. So we're going to do velocity of 20 times 2.85. That's going to tell us the range. This gives us 57 meters. So that's how we can figure out the range using a horizontal velocity and a time.